Good afternoon, everyone. It's quite loud now. It's not too loud. Okay. Okay. Thank you to everyone to be here this afternoon with us. So this afternoon we'll be having the second part of the crop monitoring training course under the CopPhil program. So for some of you who attended the first training, the theoretical part was done in February 2025. If you were not there, you should go, and we will directly give you the information to go into the CopPhil digital platform. On it, you'll be able to find all the courses that we've been doing already, and all the material will be available and accessible there for your use. Before we start this training today, so we want to welcome you here. We're happy to have you here, and we will start by listening to a few words from the European ambassador. As you know, CopPhil is a program financed by the European delegation under the Global Gateway Strategy, and it's implemented by ESA. And we are working here to this in this implementation with FIRSA and DOST. And this allows us to provide all these training courses about the different services that we are developing. And just before we go to this short video, so this session will be recorded. This will allow all the participants that could not come or were not invited today, because you see this is a small room, so everyone can go back on the CopPhil Digital Campus to access to the training and the recordings. Okay, so now let's listen to our European ambassador, Massimo Santoro.
European Union ambassador to the Philippines, I am very honored to represent the European Union, made of 27 European countries with a shared commitment to peace, prosperity, sustainability, and democracy. The European Union is not just a political and economic union. It's much more. It is a global partner which values cooperation, inclusivity, human rights. Here in the Philippines, the European Union has been a reliable and consistent partner for over 6 decades. We support a very wide range of initiatives, from promoting peace, good governance, human rights, to enhancing common security in a complex and geopolitical context, advancing digital innovation, trade, disaster risk reduction, green economy, and much more. This long-standing partnership reflects our deep commitment to working hand in hand with the Philippines in building a more sustainable, resilient, and inclusive future where no one is left behind. In the Philippines, a country especially prone to hazards and the consequences of climate change, this means supporting initiatives which create real opportunities for communities, foster innovation, build resilience in face of these global challenges. And in this context, the Philippines stands to benefit immensely from the integration of Earth observation technologies. This will strengthen the country's capacity to address climate and hazard-related vulnerabilities, and will support biodiversity conservation. I am very proud, therefore, to introduce the CopPhil. CopPhil is a unique flagship initiative of the European Union Global Gateway Strategy. It is managed by our team here at the European Union delegation, and it is implemented by the European Space Agency in partnership with the Philippine Space Agency and the Philippine Department of Science and Technology. CopPhil promotes the use of free and open satellite data from Copernicus, the EU space program's Earth observation component, through activities including the establishment of an IT infrastructure and Copernicus Mirror Satellite for accessing and processing Copernicus satellite data, on biodiversity, on forest management, on agriculture, for example. This transfer of data is reinforced by the CopPhil training program, for which we are very excited to cooperate with institutions across the Philippines. These courses build a shared understanding of value and the practical applications of Copernicus satellite data. Together, through CopPhil, we are advancing a partnership which empowers the Philippines to become a central hub for Earth observation in Southeast Asia and supporting its path towards a more sustainable and resilient future. I would like to sincerely thank all of you, the participants, as well as our partners and stakeholders who have made this training possible. Your dedication, your enthusiasm are the foundation of the CopPhil success, which is a very important joint initiative together with our Philippines counterparts. Let's remember that our progress relies on ongoing cooperation, shared learning, mutual support. The challenges in front of us are complex, as we are very aware, but it is united in purpose that we can build lasting solutions. Thank you very much.
Thank you. Okay. So before we enter the practical session of today, just to remind you that under the CopPhil program, so we have this training series on all the Earth observation pilot series that we are developing under the CopPhil project. So there is a round of theoretical course that happened from February to March 2025 on all the different cells that we are developing. So one on ground motion, one on land cover, forest, and crop, which crop is actually part of this second series. So you will have dedicated session on forest next week. We will have dedicated session on forest next week. So like as today, we will not be able to accommodate everyone, but we're trying as much as possible. So if you have registered, we are about to send the invitation and confirmation today or tomorrow. Then the crop I mentioned, the land cover, which is combining the three information. And then finally, the last service on the benthic habitat mapping. And for this, we will be conducting the practical session in 3 weeks' time. So all the theoretical series or session have been are finished now, so you can find them under the CopPhil digital platform. And we are now starting the practical with the crop today. So this is the access, so you may scan this one if you are not registered yet on the CopPhil digital campus, or you can just, you have the information on the email, or you can just ask us again. So this is where you will find all the material for the trainings, the theoretical course, the practical course, the applications to come. And this will allow you to access a certification at the end of this training. So for all of this training series that are being conducted, we offer a certification process. So for this, you have to register to this campus online to go to the training material, to take the quiz, which is after the end of each of the session, to validate it. And when this will be validated after the theoretical, practical, and application, you will receive a certification for this course. This is just an example, just to show you what you will find or how to navigate under the CopPhil digital campus. So accessing to all the material. And just what I was saying about the CopPhil training certificates. So there's the process is, of course, to first apply to the training session, which you've done because you are here. Then attending the course or taking them online, and finally getting this this quiz online to validate the course and get to the course certificate. For your information, CopPhil will be present at the Philippine Space Week in August. we are organizing and we are preparing some events related to this training. So the last application training will happen from the 4th to the 8th of August, so just before the Philippine Space Week, and we will be able to award and to provide the certificates during the Space Week. This is for the introduction and the formalities. Now I will give the floor to Dominic, who will present himself. So Dominic, well, it's from Geoville. He's part of our consortium working on the crop mapping, coming from Europe just this week for the training and for some dedicated technical meetings with the stakeholders here. And he will now present you the crop mapping practical session.
Yeah, so my name is Dominic Hewitt from Geoville, which is based in Austria. And yeah, we are a partner in the project, CopPhil project, to work on the crop mapping and implement that. We are using Centre, which is also an ESA project. So yeah, we'll be going in through Centre system a little bit. Yeah, so the agenda will be sort of, yeah, just a quick introduction. And then we're going to talk about creating and uploading the area of interest into the Centre system. Then go through what it's doing. So once we upload the AOI, it will trigger a mass download and pre-processing of the indices and everything from the data, time series of the data. So we'll just have a quick look into what it's doing, but a very basic rundown. Then one of the main things, important things that the users will be needing to do is prepare the input data, the in-situ data that the training requires, or the model requires to train. And then how to upload this and trigger the crop mapping processor. We'll have a look at what the random forest the Centre system uses, which is random forest. So we'll just have a quick run through of what that does, and so we know then what to expect from it. Then we'll look at the results and how to interpret those. So just a quick introduction, Centre Stats. Does everybody know what it is or have used it before? That's right. So it's a system, as I said before, it's an ESA initiative, and not much of this is too important, but it's free and open source. And basically, it is a program that does crop mapping at this stage. And it facilitates the download and the pre-processing and everything to make it much easier. So it's basically from start to finish application. Another thing is it's based around using Sentinel-2 data, so it's free. And also it keeps the costs down for computing power by using a robust but simple algorithm. And another main point is the estimates or the timeliness of the estimates. Also, so you can do historic predictions. You can also do it for the current state if the image data is available. And you can run it for a year, a season, a month, whatever is required.
So just a quick one. So this is an interactive session. So please don't hesitate to raise your hand, have a question if there's something is not clear. We are really here and we have a small amount of people, so it's great to objectively to have some discussion and please feel free to ask.
Yeah, exactly. And I will not just be sticking to this presentation in presentation mode. I'm going to be sharing my whole screen, and I'm going to flip between the notebook that everybody will make sure everybody has access to, and also just QGIS to a little bit of visualization. So I'll be yeah, going back and forth. I'll also maybe walk through the room, make sure everyone's kind of can access and got everything we need as we go. So it's going to be not very, it's informal, let's say. So yeah, just a quick overview of Central Stat System again. So you upload your AOI, that triggers the pre-processing, which is normally nothing we have to worry about, but we'll still go through what it's actually doing quickly. In situ data, preparation of that from different data sets, making sure it's all in the right format and how to upload it. And then finally, how to look at how to run the crop classifier. And it's not there, but looking at the results and how to interpret those and the accuracies. All right, so now it's a good time that we're going to see if we can look at the notebook. So has everybody able to get this far to see the notebook in a browser? You don't need to download anything. So just if you click on the Drive link, you'll see something like this or this. Has everyone got that? Yeah? No, if anyone says no, we need to send you a link or something. And there's definitely nobody actually, like some people might not, but nobody actually. That's for sure. And the next thing is to click on the notebook, to the one on the bottom, yeah. And I'll double click it and show that sometimes the problem is that your account hasn't got Colab extension installed. So
We should show like this. If it doesn't, we need to.
So what we need to do then is we go back to the page. I think. Then we right click, open with. And Colab won't be there, so go connect more apps. If you click on here, then we just search for Colab. And then I think it's collaboratory. So if you search for this, then you would install this first one here with the CEO gold. Okay, maybe use that reset this time. If anyone has an issue after that, just reload the tab, refresh. Wait. Sorry. Yeah, that's it. Okay, so this notebook doesn't really, you don't need to, actually, I should explain what a notebook is if not everybody knows. So a Jupyter Notebook is just a way to document or share your work. I often use it just for sort of data exploration or something like that, just because you can document what you got as you went through. And yeah, the great part about it is you can run a code example and then just visualize straight underneath, and it's got sort of a flow as you go through. And you can also use Markdown, which you can see is the top one, just to sort of annotate as you go, do headings or comments, things like this. And so I chose to do this training session with this notebook because we can kind of go through it start to finish. Whereas if we did some of these things in QGIS or something like that, it can, some things might not work depending on if we've got different programs or different versions. And it's a bit slower. Whereas here we can just execute the code, it'll always be the same. It should work for everyone. So what we want to do is we're going to go through the notebook and we're going to click on one of the code or the first code cell. They're always called cells. And we can either click run on the left. There's this button. And we're going to just click that. Alternatively, you can do Shift Enter. So this first one's just installing on the instance. So we've got like an instance on Colab, so a little computer. And it's initialized for us. Everyone's got their own. So now we're just installing the packages that are required. So that will take just a minute, I think. Then the second one, because we're using Python coding or programming language, we're going to import these libraries. So we're just going to run that one. So I'll go Shift Enter, and then it automatically goes down to the second one. That's working for everyone. Could be. I've only got one more hurdle. Well, there's a few hurdles that we had yesterday. So now we're going to mount the drive or the folder that this is in, but we need to mount it to access the data. So we're going to run this one. And it's going to ask us for permission. And it does this every time. So I choose my account. Say continue. You will have to, I think it's just the first one, click to access the files. Don't worry about the other ones about photos and things like that. Generally, and then click continue. And then it's going to mount the drive and it will turn up on the left. Should. There we go. So now I can see drive. If it doesn't work, it should be working. Later on, there might be an issue. Yeah,
It's not working. You have trouble with the number 3 today?
Yeah, I think it's the next one, or it's just a string, so it doesn't try to do anything. But the next one might not be able to find it. Yeah, let's try and run the next one, which is just showing when the path to the data. So actually, it won't throw an error because it's not trying to access it yet. But then, so first thing we're going to look at is how to create this AOI and how I did it for our latest test case. So when you run this one, the next one about the S2 tiles, so Sentinel-2 tiles, it's a shape file. you should hopefully see a table show for each geometry file.
You might have issues, but if you do have issues, you can source it. It's just. Yeah. All right. Okay, that's gonna happen to everyone. So, yeah. You said, okay. That's because for some reason it doesn't like to go into the shared
Folder. So what we're going to do is go back to our the Google Drive folder, and I think you can click on this. Yeah. So click on the full folder and go organize, and then add shortcut. Everyone got that? All right, so we're going to add the shortcut, and we're going to direct it straight into my drive. So it's like the root. And so it's going to put a shortcut straight into my drive. Okay. And then add. And that means when you go back to my drive, which is for everyone their drive, there'll be a shortcut, and I've just added an extra one. So there'll be this one here with a little shortcut sign. So that means now it should see it straight in the drive. So when you rerun it, now try and rerun this. You might have to rerun this drive.mount, this first one, and do it to be safe. So run that one, the next one, and then he has 2 tiles. And I always have to do this test to make sure. Working?
All right, perfect. Well, yeah. All right. Cool. That was the main hurdle that can go wrong sometimes.
Okay, so this first one, I just wanted to load the Sentinel-2 tiles. If we run the next one, we can also visualize that over the Philippines. And the reason I just did this was so we are all familiar with what Sentinel-2 tiles are. So when Sentinel-2 data is prepared and downloaded, it's always in these tile formats, which means you can always get the same area. If you get multiple dates, it's always over the same area. And CentOStat works in using these tiles. So when we create an AOI, or area of interest where we want to work, CentOStat will automatically know which tiles we're looking at, or when the tiles over the area we're looking at. So if we have an AOI of 2 tiles, it's going to download those 2 tiles every time for the whole time series. And unfortunately, some things can take a little while because Google Colab these days, they've limited the resources. It used to be much, at least I remember it used to be much faster. Now I think it's more popular. So it lowered the disk and RAM that you get per instance. So here's what you should be seeing. So it's also visible. You can also see that on QGIS, which I might do now. So a similar thing as you can see here. If I zoom out, we've got all these tiles. And they've all got names. And you can see our in-situ data, which we're going to go through in a minute, is kind of in the overlap between this tile and this tile. So this is the overlap area. And actually it's shaded here, so it looks more obvious. So that's just to explain how it always works in these tiles. So we're always going to be downloading, or CentralStat will be downloading these two tiles here, or to get the in-situ, not the in-situ data, the satellite data. So we already know beforehand the names of the tiles that we're going to use, and we're going to use these. We're going to extract these from the file above and make them our AOI. So we're just going to run this cell, and then the next one is just zipping and saving zipping the file, or creating a zip file, because that's the format that CentralStat needs. So we're going to do that. And what you should see on the right, if you go to the folder icon on the left here, that's not the right, it's the left, then you will see this isn't in the drive, this is in the instance at the moment, in the instance as it's running. So here's the AOI here, and you would need to download that if we were going to upload it, which we're not actually going to do. The next one, I'm just going to load, DF stands for data frame. And this is just loading the first file of the in-situ data we got. So this is the crop data that I was given a while ago. I'm just going to load that for now, we'll use it later. And finally, it's just another visualization. You don't have to worry too much about the code in that. We just execute that one. And it's going to produce a map, and it's going to show these two tiles now. They've been merged together to create our AOI. And then I've just put in this data frame of our in-situ just to see, make sure that the AOI is in the right area. And actually you can see down in the bottom left, you can even zoom in this map. There's a few down here that are not going to be in the AOI, so we need to click them out later. Everyone following along so far? Cool. So here's a screenshot of how the menu when you want to add a new site, which is the first thing that we need to do when we go into CentralStat. I'm going to actually show you what that looks like. Actually, I should mention this says CentralCap. That's another program very, very similar, actually based on this, or CentralStat is based on CentralCap in a way. My browser has cached this, but if I went to, this is a Mac, so if I went to Safari and went to CentralStat, this is how it will look like for everyone. But I'm going to go back to this one, just because I've got my password and other things saved. So the first thing I do and see are the sites. Sites are the AOIs, or where we upload our AOI. So we'd go create a new site. And your AOI may be already decided. It might be a municipal boundary or a province, something. So just for us, for a test site, we just quickly created one like this. So I thought I'd show you that too. But it needs to be a zip file of shape files. And then you would just upload it here. And then choose a site name, whatever's applicable. Mine, as you see outside here, is test site 1 and test site 2. So once that's done, you would then edit and you would add your season. So here I've got I've got 2 seasons and I can just choose one or the other. Edit, turn that one off. And save. So then you got 1 season, and you can choose, like I said before, you can choose a whole year, but that's not ideal for here in Philippines. We have usually a few crops per year. So you'd probably choose some dates based around, planting, harvesting date of that one crop. So it might be just a 3-year season, 3-year season, 3-month season, for example. So once that is uploaded, the system will start automatically pre-processing. So you will have the data already linked to the system, whether that be a DIS or a network drive if you've already got the data downloaded. For CopPhil, there will be a mirror site, I think, of the data repository on a DIS or CreaDIS, it's called. So this will be directly linked. So downloads and everything will be not quite instantaneous, but quite quick. So it will be doing some pre-processing. And just to give you kind of an example of what that is, I've added this section here in the notebook. So we're going to try and explain, understand quickly what it's doing. So very basic. Some of you who work in remote sensing or GIS will find this boring and simple, but it's still good to get everyone on the same page. So the first cell here was just a little function, just because the data I downloaded from Copernicus Hub, which is just a manual way of downloading, just from the website, just downloading a few images. For some reason, the paths within the file are slightly different. So I just made this quick little function just to deal with that. The next one, when we execute this one, we'll unzip these files. So normally when I downloaded it from Copernicus, it'll be a zip file. So I'll unzip those. And that's all this next cell is doing. So if we execute that now, we will see a satellite data folder pop up. And that will slowly get 3 save files, they're called. So the files are called .save, which is the standard way of storage of these files for Sentinel-2. Is that what we need for everyone? All right, so you can see on mine, at least, I've got the 3 files now. And again, Sentinel will be getting every image in this season that you specified. So per month, that's normally every 3 to 5 days, so 4 or 5 images. And if you did it for 6 months, that's, times 6. So it'll be a few images. Then what we're going to do is, I think this is just making sure it's there and just choosing the first folder, because the first few images we're going to look at will be just one image, and later we're going to make a composite. So run that one, and then this one is just, we call it a dictionary in Python, but it's just putting together a list of the files. So we know we're labeling each file as what band. So those we're doing blue, green, and red. So we're going to run that one. And then the next one, we need to fill something in. So we're going to make an RGB image, which is red, green, and blue, which is a normal, for any color image. So photos or anything like that is usually just made up of a red, green, and blue band. So just to make it a little bit more interactive and stop people from barging through the whole notebook and just running everything and then saying I'm done, I put in a few little tricks to trip people up. So yeah, if it's RGB, that's red, green, blue. We need to add the band names to here to load them, and then we're going to display it. So that means we're going to add up here, we've got the names here, so that's blue, green, red, and what the bands are in Sentinel-2, which is band 2, 3, and 4, and that's how they're labeled in the file. But I made sure that they're linked together. So we're going to go RGB, which would be red, green, and blue. And then that's all we need to run that. And this first one is just so, yeah, you know, what bands are, what they do. And yeah, how to interpret them. So RGB, again, is just the standard color, at least the way we see it.
How's everyone hearing about it? Or is it still everything? At least I know nothing's come up with a failure. That's just put this out. That's fine.
So most people have this already, if not very soon. This is the one image, so one Sentinel-2 image, and you can see this is actually a very good image in the fact that there's not so much cloud cover, so that's quite, apparently in the Philippines here is pretty lucky to find. But still, there is cloud cover. So we want to find a way to remove this. And that's why we're going to do a composite later. But before that, I also wanted to show this was RGB. But I also wanted to show how you can use other bands also to get some information, and sometimes easier to interpret depending on what you're looking for. So what we're going to do is then add the near infrared band, which is band 8, Sentinel-2, and this one's just adding it to that list or dictionary. And then the next one doesn't have anything to trick you, it will just run. And so this is replacing the blue band with the near infrared band. So it's not going to look natural, but we're still going to see some interesting elements here. It's very slow. And actually, I might even move on while we're waiting for this, because I think everybody's at the same stage anyway, if not already further. So we're going to go to the NDVI, which is a combination of two bands, which is, okay, that's already done. Okay, then I'll talk about this then, is just quickly, so it obviously is not the natural way things look, but it's called a false color image, or false, it says composite, that's not true, it's just one image. But immediately what you can see is the green vegetation, so forests, in this case mostly forest, also some crops or something through here, is red, and that is the infrared band, reflecting receiving the reflectance from the forest, from photosynthetic material. But again, we can see the clouds are quite obvious, and we want to get around that. So back to the NDVI. So this is comparing, we're using that near infrared, which is quite important for vegetation studies, and also the red band. And this is a very standard, I think most of you would know about NDVI. It's one of the most standard used indices, the go-to, I'd say. And it's used as a measure, or can be used or described as a measure of greenness of the vegetation of what's on the ground. So again, here I've got just a little trick here to stop people. Hopefully you've worked it out. So it is the near infrared band and the red bands. So bands 8 and 4. And if we go up and we remember, that's here NIR, and the other one was red. No edge go. So we just put that in here. And and red. But before we run that, it won't work, because I've also commented out the calculation of the NDVI. So to make sure you guys see how it's actually calculated. So what we want to do is uncomment that, which is the hash. Take that out. That means the code will run this line. And then we have to replace these band names. So this is band 8. We have to replace this with what the variable is. And be careful here, because these are actually first and second. I've saved them as first and second. I could have called it NIR and red, but that would have given you an obvious clue. So I've just called it first and second. So here, band 8, which is NIR, which is first. So it's saved as first. So we'll put here first. And here second. And again, first and second. So NDVI stands for Normalized Difference Vegetation Indice. And what that gives you is the values normalized, and it's then between -1 and 1. Although most of the time you'll see just from 0 to 1. So now we can run that, and it's going to calculate, it's going to load the two bands, calculate the indice, and then plot it. Everyone got that super? Or just go. Actually, what we can also do while we're waiting is run the next one. And I'll start that now. And what that is doing is creating a composite. So this NDVI, again, there it is. The next one's going to do a composite of NDVI, and I'll tell you what that is after I explain now or show you the NDVI. So you can just see from the scale on the bottom, the areas of water obviously have zero vegetation, so that is basically around zero. And then you've got areas of high vegetation, whose forest areas are quite high. And that's why it's quite a robust way of looking when doing any study on vegetation, basically. Classifying between different vegetation types or land covers or anything like that, it's always a good starting point. Yeah, as was pointed out, we can still see the clouds here. Up the top right, you can see these dark splotches. Also on the bottom, all these dark splotches, clouds. So one way we can deal with the clouds is to create a composite. So take more images along the time series, close together. And when you have an area that doesn't have the cloud cover, we can take the values from that one and disregard the clouds and then sort of superimpose them all. I'm just doing 3 images. Generally, it's quite often that I'm not sure what CentralStat does exactly, but generally they go around a month or 10 days even, is the sort of time period that they take all the images and then do a composite of it. There's a few ways to do the composites. To save on RAM for this notebook, because it doesn't have so much, what I did was I did a maximum NDVI. So it loops over each of these files, calculates the NDVI, and takes the maximum NDVI. It takes the highest NDVI at the time. So if it's already looked at one, it's going to take the first image, it's going to take all the values because that's the first one it sees. And then the next one, if the NDVI, say for 1 pixel, is higher, it will take that one. Otherwise, they will just leave what it found last. And this just reduces RAM because it just does it one at a time. Another way is to load everything in at once, and you can do some other metrics or statistics, but just having 3 images on this notebook was too much. I should also mention here in the code then, yeah, I forgot. So this is calculating the NDVI, as I said, and it's saving it. It's not, there's nothing here to display it. That's the next cell. So we'll run that one. And this will display it. So we will read, we just saved it. Now it will read this composite, which is, you can see over the left here, it's actually saved it. So now it's reading it and we'll display it. All right. I guess everyone can see this or will soon. Maybe I should check. All right, this I get everyone got it or we soon. Yes.
You have to replace the value there.
I did, yeah.
Alright, so the thing I wanted to show you then is these ones with the clouds in the NVIDIA single NVIDIA image.
Now we've managed to get rid of them because we've taken a maximum NDVI, and the single image, we see that the NDVI was really low where the clouds are. So that means that when you get an image without the clouds, it's going to be higher. So that's just one way of generating a composite. Another thing Cenfostat is actually better at and will be doing will be cloud masking. There's two ways to do it, and they're called fmask and Maya. And that's an algorithm that can detect clouds. Like it's usually quite advanced AI detecting the actual cloud areas and masking those out. And that's generally a better way to get these images cloud free. Also for different bands. So for NDVI, it was easy because clouds have a very low NDVI. And so when we get an image that doesn't have it, then it can save anything that's higher than 0. For other bands, or single bands, that's not so easy. So that's when the masking comes in. All right, so that was just, I think everyone's got there now. So that's just explaining what Cenfostat is doing. So it's down in the images, these tiles, for the whole time series. It's creating indices, not just NDVI, there's a few other ones. Also, it's gathering information like LAI and other biophysical parameters for this area. And so our job then is to produce the in-situ data.
Is the tool that could be included and packaged in the CopPhil Crop Service. So when you might see the information in the vertical parts or in a general presentation of CopPhil, but for the crop mapping, we are relying on the Cenfostat tool. So now the link is showing all the steps that are the process of the calculation of the crop mapping, but at the end, when the CopPhil crop map itself will be available, you will not have to go to this step. This will be included in the, I would say, like a black box maybe, and it will be running this type of algorithm in the background. But just to show you now the process, what the Cenfostat and the crop mapping service will be used.
Thanks. All right, so this next section is an example of how to prepare the data and get it in the right format.
On the contrary, not this part. Preparation of the data, you will have to, in any case, because this is all the preparation of the in-situ validation data that your algorithm will need, either it is on Cenfostat or on the CopPhil crop mapping service. This task is something that you will have to do. Preparing the data is something that you cannot avoid.
Yeah, thanks. I might mention it here now first, because this is the important takeaway, is this is what Cenfostat needs from the in-situ data. So you need one shapefile for the geometries, and that's just simply got the parcel ID, which can be 0 to whatever. Segment ID is just a formality. I think it's used in, or it's to be used in other processes, but it needs to be there or the system doesn't accept it, but it can just be the same numbers. This parcel ID is similar to sort of databases. This parcel ID is, I've forgotten the name, there's a phrase. Basically, it's the column that's linking the two. So we've got a CSV, and this has the information about these parcels. So we use that parcel ID, which is the same, number, and then we've got the crop code. And these crop codes are specific to Central Stat. So we need to get I'll explain it later. We need to get our in-situ data to match these codes. And there's a document, there's like a, I'm not sure, it can be any format, but there's a list, let's say, of the crops and the code to use.
Some in-situ data samples that are provided by companies in the Philippines. But when you do some modeling, this in-situ data is the data that you get from the field. So having the parcel identified and the crop identified on the field, knowing where is corn, where is rice, where is all these parts that you wanted to have to see in your final data for the transformation. And now it's the specific task, so it's possible to collect the data. And now for the different task, it needs to be formatted. The table, the data needs to be formatted in some specific colors, so that Central Stat can read the data that you're inputting and working the data.
Yeah. So, for example, you would have some kind of in-situ data like this. It has to be geo-referenced, and it needs to have the crop code, and that's all that it needs. These are
the data that you're using.
It's part of the data. So I've got 3 data sets because in a real world, we need, and I'll talk about this later too, is we need all crops that are going to be in the mapped area. We can't just choose one. And I'll talk about that with the random forest algorithm. Yeah, in this case, we just had corn, onion, others, and rice. But we also got sugarcane from another source, and also land cover, so forest, urban, and other classes like this, which need to be mapped as well. We got that from another data set. And so we need to merge, we need to get these in the same formats, do some data wrangling and get it looking all the same in one data set, and then we can upload it.
So when on the GIS, so these are the colors polygons are the data in the map. So for all the others, the white one or the non-colored one, so this is where the algorithm will actually have to guess what is the crops under this one.
Yeah, I guess we'll talk about, so the random forest algorithm, I'm going to get into it later, but the random forest algorithm maps what you give it. So you need the in-situ data to encompass all the crops that you want to find, but also the ones you don't want to find, but needs to be defined, because otherwise these areas will be classed as one of the things that one of the land covers that you've put in the data set. So I'm trying to think of a simple, actually, yeah, I'm trying to think, I'm getting lost in my, a good example would be, let's say we didn't put corn in. Ignore that. Let's say we didn't have corn. We mapped an area. We added rice. We had coconut. We had forests. That's enough in the in-situ data. When we do the mapping, this corn, the algorithm will, it has no idea what corn is. So it's going to assume it's the next closest spectrally, how it looks from the satellite, which will probably be, I said coconut. So it could be coconut or forest. It depends on which one looks similar, which one the algorithm decides. So that's why it's important that we need to put corn in. And it's also quite a widespread crop here in the Philippines. So that would be a mistake not to include it. I think that's what I was saying. But also on that note, sometimes you can't add everything. You can't add every little crop. So you can group them, but as long as they're similar. So say, for example, some really small holding kind of crops. Yeah, I'm not sure, but just some small things that also are hard to identify and can be grouped, but don't do things that are very dissimilar. So for example, you can't just put everything in the other class, like the small holding crops, and then some rocky areas with no vegetation, and then water, and then forest, like a different type of forest, because they are so different. The algorithm will just be confused and kind of reduce the error, go for the middle, which then will probably be a lot of areas that were classed as that. So you have to encompass everything that's going to be in the area trying to map. You can be vague in some things, but not too vague. So you have to have some knowledge about what it is you're looking at and group those appropriately, if that makes sense. And we might go through some examples later.
Any question?
All right. So I think then I'll go through how I combine the data sets. So we're going to go through here. So hopefully we've still got this df variable loaded, which was the first data frame, which is what we just saw in QGIS. So if we load that, and head just means we're going to look at the top 5 entries. So we can see this is the data set we got. We can see here along the top, crop C has what we're looking for, the class corn. And that's all we need from this data set, really. We should also use the planted date, so to know when, to make sure we're mapping, it's in the season that we're trying to map, because it will be counterintuitive if we told it was corn, but it was corn 2 years ago, and that's not anymore. So these next few cells are just kind of doing the data wrangling. So we can see there's this class, but that's just a number, and that came from, we're not sure where it came from. Oh, I'm not sure where it came from. So 1 to me doesn't mean anything, because we needed to map it to the SemperStat class. So this one next is just dropping that class, because we're going to use that name class later. The second one is making a new column called crop type, and it's taking what is in cropland C, which was corn in that case. But also what it's doing is, if further down in the data set, these might be empty, and that's because it's from another data, it's in the same data set, but someone has merged it. And the crop type name that we're looking for is actually another column. So this line is just saying take the name from crop C column, but if it's empty, take it from cropland 2 column. And that I found just because I was looking at the data and noticed that something's missing. So if we run that one, and what you can do is always go back up and run. So we've updated this DF data frame. We've added this crop type, and you can always just go up and look at it again. So we'll run this one again. And then there'll be all the way on the end, there'll be this crop type, which takes the one we were looking, the name that we're looking for. So just some quick general housekeeping here. We're going to replace corn with maize because it's the SemperStat name. And we're going to change others to unknown because it's also a name, SemperStat name. The next thing was I just made a little function that does a fuzzy match, which basically checks the strings or matches. I compare 2 strings, and if there's a match, similar, like it's similar but not exact, so there might be an underscore, there might be a space or a slash. It gauges if it's matching or not, and I say if it's got a score of 50 that it's a match. And that's just a quick way to match different columns with each other. It's not always perfect, but it depends on the data set. Sometimes it's perfectly adequate. So we're just gonna, that's not gonna do anything, that's just defining it. And then we're gonna do it later. This next one, the CopDict, is the Crop Dictionary, so I'm just gonna load that in. And that's the Centre Stat names. Actually, what I can do is you can add another code. And I'm going to quickly look at what that is. So this is what I was talking about, the Centre Stat names. So this was provided by Centre Stat to me. And so it's got the classes, which we're going to make sure they match these classes exactly. And then later on, we're going to match it to these crop codes, which is what we're going to, when we got that, the crop code and the geometry, that's what we're going to upload. So back here, got the crop code. Here, yes. Somewhere. I promise you. I was actually looking for it the other day. That's that. All right, this next one is yeah, just matching the names. So this is the function that I just defined up before. So it's just going through the names and matching the closest Centre Stat name and making a new column. So we're on that one. It's going to add a new column to the DF. We can always go back up if we really I'm not sure if it's worked or want to check what it's doing. Run this one again, and you can see it's got crop type renamed, and now it's maize, which was already maize, which is because we already changed that. So another way to check is just to check the unique labels. So we can run that one just to make sure everything's in there. So we've got maize, unknown, rice, and onion, and the Centre Stat name is rice including shallots. Sorry, onions including shallots. And then, yeah, I've just added another cell here. We can have another look if we wanted to, or we can delete that. Not needed. And then finally, for this data set, we're going to just take what we need. So we're going to rename this crop type remaster we just made. We're going to call it class. And then we're just going to take class and geometry. And we're also going to reproject it to make sure it's all the standard CRS. We run that, and then we can have a look at it again. This can be, so this is printing it, or you can do .head to show the first 5 or even 10. And it's the same thing. So we got the class, geometry, and that's what we need. Almost what we need, actually. We need this class to be the numbers, not the name. And we use that dictionary to map it, which will be done later. So then, as I mentioned before, we need all the other classes, and that's not always in one data set. So we had another data set we got of some samples of land cover. And we can see this was provided with the data. We've got the name, and in this data set, what it's mapped, what number it's mapped as, because it's a raster data set. No, it's a shapefile. Okay, never mind. Anyway, it's got a class assigned to it as well. So this is just going to load. So this one is going to load the shapefile. And this one is, again, mapping it to Centre Stat classes. And we can look at that one. We see we've got the geometries again, and we've gone from the class ID here to what the Centre for Stat classes are. Or no, sorry, that's the one that was provided. Then we're going to, this one maps the correct one. Then again, the one after that is just general housekeeping, changing names, and just taking the class and geometry. So we'll run that one. And then the next one just shows exactly what we had before. So now we've got the first one and the second one in the same format. We've got class, geometry. Finally, we've got, okay, we don't need that crop dict. That was just what I loaded before and you saw before. So this is the other data set, final data set that I used in my initial training run or initial run of Centrostat. And this one was much more simple because there's only one class. The whole data set is sugarcane, so there's not much to wrangle around. So we just read the data set. We made sure it was the Centrostat class, which is here sugarcane. And we already know that. We don't need to put in some code to make sure it's the right one or to look for the right one. We just know it, there's only one. We take only the class of geometry like before, make sure it's the same CRS. So we run that. And actually we can even, and I didn't have it there, we can quickly look at it to check that it's going to be in the right format as well. Yeah, class geometry. No. Yes and no. I mean, what I could do is I'm going to merge these and save it. I could download that and put that on the QGIS. Or those three data sets, I can just show you before I merge them, which are still here. Then I'm not sure if I can zoom to this. Yeah, okay. One of the data sets has something all the way down here, but we're up here. So this is everything in our data set. Actually, so I'm not so lost on the map. I'm going to zoom to the polygons we had before, which up here. Here's the sugarcane data. That one's pink. That one, yeah, the darker pink. Yeah. So that's flashing is the sugarcane data. The polygons are up to the right. And then the land covers are the bigger ones because they're much easier. They're the urban forest, mainly urban and forest. I'm sure there's some others in there. We could, yeah. Oh, we can even go back quickly here. Just choose a place. Can be anywhere. I'm just going to quickly check or just run this code. Actually, I won't do. I'll add a code and check what was in. Sorry, I got confused. It's already there. So that was the land cover data set. We can do .unique. And did I spell unique wrong? It looks wrong. Or is it? Should be. Okay. There we go. Yeah, so we can see the land cover has these classes. So then we've got those three data sets we put together, or we haven't put together. We've got them in the same format. Now we're going to combine them. So we just do a quick check. Yes, they've got the same columns, same data type. So now we're going to concatenate them. So join them on one after the other. Then we're going to basically just set the index. So we're going to reset it, rename it to the parcel ID, and then just set the index to a parcel ID, which will be starting at 0 automatically. And that will be our index. Choose nothing. Okay, just skipped ahead. All right, so now I've merged them. We had a look at it, still looks right. We looked at the unique values. We can see they're all there now. And what this line is doing. Now we're taking the Centre string name, so maze, forest, whatever it was, and we're mapping that to, as in we're using the dictionary to look at what code was assigned to it and giving it the code instead. And so we run that. We will notice that this new cop code is there instead of the name before. And that's the format we need for the shapefile. So now we've got everything wrangled into the same format, into the same data set with the right columns and the crop code. Finally, I'm going to, as you saw before, there was some data set all the way down in Mindanao. We want to take that out for now. So we're just going to clip it to the AOI. That gets everything else that's unwanted. And then we're going to save it. This one says, so it's to file. We're going to name it test2 in situ. Labeled it UTM, just so we know what's here, that it's in a UTM CRS. And 51N is the, but it's also referring to the CRS. And then the next line is just zip it and remove the files outside the zip after it's zip. So we run that one. And then hopefully we'll have this test2 in situ geoms come up. Yeah. So that's created, and that's what we're going, that's one of the files we're going to upload in situ. Yes, it has to be in the right, it has to be in the same area because the central stat is downloading all this data for these tiles. And if the in situ data is outside that area, it's not going to have any information to extract for that area. So it has to be, your parcels have to be in this area that you've defined that it's downloaded and pre-processed. And then finally, we need to make that CSV file. So go back to here, you see we need this matching CSV. So that's quite quick. Well, in this case, it's quick because we need to add these columns, but for the mapping, we don't necessarily need them. Or there's other services that will eventually be implemented where this will be important. But for now, for just mapping, it doesn't need to know any of this information, but it needs to be in there, just a formal check that it does when you're ingesting the data. So we're just going to create those columns. We added year because we know it. Top quality is, I think, just 0 and 1, so I just put in 1 to say it's all right. So we'll go back to it. So before we created our in situ data, we've already had the system pre-process the S2 tiles or the time series data. That's already been done. So the AOI obviously has been done too. So now we upload the training samples. And I'm going to show you this again on the actual interface as it is at the moment. As mentioned before, this is the sample stats interface, but the CopPhil interface, which hopefully you guys will be using, will be similar, but much simpler. In theory, it will be much simpler. So to upload this in situ data, we select our site, go to edit, and then there's just a big blue button that says upload files. And then you would upload this data that we just made. So the geometries are obviously the zipped shape file, that's the geometries. And then the CSV files are the statistics. And you would put these in here, upload them, click upload, and that would go into the database of the central stat system. And then the system is ready to train and predict the crop type over the whole area of your AOI, but not only your AOI, these two sentinel tiles. So to do that in central stat, you would go to the dashboard, you would choose crop mapping. You would schedule a new job. And then you would give it a name. I've used this one previously. The site, so the site you've just uploaded, say this one, the season that you've defined, test season, and then schedule we just want to run once. And usually you want to do this, at least in the early stages, you want to do this. Even if you want to, you know how often you want to do it. Sometimes you have to wait for the data to be ready. Maybe your in-situ data is not ready yet. So it's always best just to do it once because it might be a few days late and you're not ready for it to run in its sort of automated scheduled mode. So you always just do once. And then the time, you just generally set whatever it says here, which is usually today, the day, like the start of the day. So it will trigger straight away. So then you would just click save. That would trigger the processor to run now. And then it would process, it would extract the Sentinel-2 data for each parcel. It would train the random forest. And then it would predict using the Sentinel-2 data over the whole map. So it would extrapolate. And so we're going to go into, let's imagine that we've triggered this processor, it's running. Now I just want to go in that notebook. It's not the notebook. Here it is. So in the notebook, the next section, we got the random forest classification algorithm section. And this is just a quick, very simplified version of a random forest using Python code. Just using this max NDVI composite that we made. So just one image. It's a composite of 3 images, but it's just using one input data set and this in-situ data that we created before. So it's kind of mimicking, in a way, almost, yeah, not quite mimicking because it's a very simplified version, but it's still random forest. So I just wanted to show sort of what it's doing. So if we run these cells, this one is loading that max NDVI again, in case it wasn't before, but that's fine. And also what it's doing here is what I said before, it's extracting the Sentinel data for each parcel. So that's called a zonal statistic. So it's looking at every geometry and it's taking the mean. In this case, I've set it to the mean of the NDVI image. So all the pixels within this geometry, it's going to take the mean of all the pixels. Then what we're doing here, this is just some general cleanup again, because just the way the data comes from the zonal stats function, but also some of them have no data in it. So I'm just going to clean that out. And the reason it's got no data is because it's most likely outside of the Sentinel-2 tower or just in an area that doesn't have data in the image. So it causes an error. So we're just going to run this one and the next one, which drops those geometries that doesn't have an NDVI. And if we have a quick look at it, we can see this is our in-situ data that we had before, this merged DF. But if we go all the way to the end, we've also got the mean NDVI extracted from that NDVI image we had before for each parcel. So that's, again, this is what CentralStat's doing. Then we're going to run the random forest algorithm. So here we're just dividing this merged DF into the 2 variables. So the dependent and independent, or the target variable. So the target variable is the crop, and then the NDVI is the independent variable. We're going to split the data into test and train because we want to validate the model, but we can't. We have to use data that the model hasn't seen. So we split it. In this case, 80-20% split. And then we're going to fit it here. So we've got these 2 trains the X, as here, up here, we've got the X and Y. Yep, as I mentioned before. So we're going to fit the model with the train splits. Then we're going to predict, so make a new variable with the prediction of Y using the test data of X, and then we're going to evaluate that with the Y test data, the unseen data. And when we run that, so it's going to train the algorithm and it's going to predict just on this little subset that it kept back. And in this case, we get quite a good model. But I know yesterday we had some other people get a different variable. A different accuracy metric. And are you guys getting 0.8 or are you getting something much lower? 0.8?
Okay.
Okay. Someone yesterday somehow got 0.3. And I was a bit baffled, but we decided it was most likely because they got unlucky with the train test split. So they somehow had some unseen data that was completely different from what was trained on. And so it got a bad score. But I got, and then most of the other people in the room, unless they maybe changed something. I didn't think to check their code. But anyway, so in this case, it's doing reasonably well. So that's out of 1, between 0 and 1. But remember, this is just for the in-situ data that it was given. So it's not measuring the accuracy of the map after the predictions, where it could be other classes. This is just the data that has been given. So all the data we gave was just these classes, and we know it was correct. And it hasn't, for example, seen areas that are of a crop that it hasn't seen. So we're just testing on the data that it's basically seen, but the model hasn't actually seen this data, but it's similar because it's from the same data set. So then what we're going to do is we're going to use that model and predict on that NDVI image that we made before. These numbers are just slicing the image, so it's just a smaller subset of the image, just because, just to save memory. This is just reshaping, so doing a one-dimensional array, because that's how the classifier takes in and outputs the data, but then we reshape it again to a 2D array, so an image. We also calculate the probabilities, and the probabilities. Actually, does everyone know what a random forest is in general? I didn't really introduce that. That's because it was in the theoretical section, so I didn't really go into it before. But basically, a random forest is made up of a classifier tree. So it's just like a yes, no, splits the data constantly, putting it in another category until it gets to a point where everything's classified. The random forest is particularly good because it uses a different subset for each tree, and so it has multiple decision trees, up to normally around 100 or 200, but you can specify that up to 500. Generally, more is not really necessary. And they all these trees see a different subset of the data, and so they always, not always, but they can then decide on a different classification for this pixel. Yeah, so all 100 trees, some of them might have a different subset and decide to classify a pixel differently than all the others. And the probabilities are basically looking at all these 100 trees. I should mention that in a random forest, the classification is just a voting system. So 100 trees, 55 decide it's forest, the rest anything else doesn't matter because the majority was forest, so it's classed as forest. But the probabilities looks further into these, what everything else, what all the other trees voted on, and then the probability would then be 0.5, I think. It would be half because the rest of them, it wasn't so certain. So it was only half of the trees kind of voted for forest and the rest for something else. So it's medium confidence. And the lowest then would be if every class had the same amount of votes, then it'd be lowest confidence possible. And then we just put it into a map and we map that as well. So we run this code. And then we'll just do as I said. And then the next one is just going to plot these. So we can have a look at what we expect to see. I haven't included like the classes. I didn't include a legend because it's not really necessary, because I'll show you the actual center stat output, which is much better. But you can see on the left, everything's classed as one of the input, one of the classes we gave in the inputs. You can see some structures there, like riparian zones. It looks like there's some kind of road or drainage line on here. But in general, it's kind of noisy. It's also not very big, but it's just for visualization. And on the left, we've got the confidence. And then, so the confidence just ranges from 1, which is 100% confidence, but not to 0, because as I said before, it depends how many classes there are. So if each class got the same amount of votes, then there wouldn't be 0. It would be the amount. It depends on how many classes there are divided by 1. I think that sounds right. I also have it in the slide. But basically, it's not always, it can't be 0, but it'll be very small, like 0.25 or something like that. So that's just a quick look and explanation, so we understand what the Census-Stat system is doing. We have to remember that it's got a lot better input data because it's got a longer time range, it's got more images, it's got more indices. There's just a few tweaks and things that are done better than just, this is a very basic sort of off-the-shelf package in Python that still does a pretty good job. But we also trained this one on just one image, so we can't expect it to be very good. So then, make sure I'm not forgetting something, because then we can move on to the results. There's an example around the forest, actually. That's just one tree. So you see you're splitting the data. And then here's an example of a random forest. So multiple trees, you do a majority vote and you get the final class. No. All right, so we're going to move on to the results. So I might start, we'll just visualize the results. So before we did just a small example, but now we'll show what I got from my first run using this data. Don't need that. In the wrong place. Thanks. Yeah, so this is the first results. This is the classification. And you can see it's although our in-situ data is not the best, it was just what we had at the time. You can see it did quite well. It's a lot better than that other example I showed, which was quite noisy, because this actually used quite a few seasons of input data, so Sentinel-2 data. So it's most likely had some good cloudless images there, composites, and also used X-ray indices. And you can see straight away that it's less speckled, less noisy, so it's able to define fields a bit better. But you can still see there's some issues, and one obvious issue, which I can show maybe best just with Google Satellite, is these areas here in the middle, they look like cropland, but it's classified as rice, which potentially is correct. But there's also forest, and that's not right. And that's because whatever crop this is, we either don't have enough in-situ data, or we might have some in-situ data, but it's in a complete other area, and it doesn't look like this crop. Even though it's the same crop, it might look spectrally different. Whatever it is, it looks like forest. It looks closer to forest to the algorithm than any other crops that we've trained it on. So we can see that it's quite a big issue here, because most of the forest around here, most of the crop around here that's classified as forest, not forest. So whatever that is, we need to find out and add that crop, add more samples to that crop if we've already got it. Or just generally better quality in situ data for that crop. Another way we can look into that is to look at the confidence. All right. So now you can see the confidence. As I said before, it depends how confident the model was when it was classifying that pixel. And we're just going to quickly give it a bit of better shading. All right, so if I load this, we can see, so the light color is a higher confidence, and the dark color, as I said before, is never 0. It's 0.25, for example, in this example. And then if we go to the similar area, which I think was kind of around here, what we can immediately see is that it's quite confident with the forest. So the forest up here, it's quite confident that that's forest. But let's say we look in a crop area that it has a lot of forest here. But here, so let's try and see that generally the cropland here it has a low confidence, quite a low confidence. You can see the riparian zones and the urban. So like there's a riparian zone here, and then you've got the urban here. That's quite confident that that's correct, as in all the trees voted for this class. Not all, most. So then we know we don't really need to work on urban and forest. That seems pretty good. But what we have to work on is whatever is getting misclassified as forest. And so it's a good time now to talk about how this process is often iterative. So the first attempt won't always be perfect, because not everyone has all day or has so much time to go through the in-situ data and make sure everything's correct. Sometimes you've just got to just believe the labels, just throw them in there. But maybe you realize, oh, hang on, like this one's completely wrong, and then you can look into, you've got somewhere to look at, and you realize that this is falsely labeled for something quite obvious, possibly. Yeah, all right, then we'll go back to the notebook. So another output that comes, and this came from the same run, you get the classification map, which I just showed, and the confidence map. You also get a confusion matrix in a GeoJSON. So I'm just going to load this here. So run that cell. And then the next one, so that's loading it. The next one's going to show it. and then you get this confusion matrix. The labels don't. These are the labels actually that come from the central stat output, but I actually have a better example in a slide where I've actually got the classes, so it's much easier to. This slide, for example, has the classes on the bottom, and it's a bit small, unfortunately. But basically, it's exactly the same. Just replace the numbers with classes. So you have, yeah, and I can give an example of what to look for here. Going across the diagonal, these are the correctly labeled classes. So, and I've got it labeled here. So we've got the predicted labels. This is what was predicted compared to what was really there. And you can see, for example, just trying to think of an example. Last time I used maize. So what was predicted and what was true. So it predicted a pixel as forest when it was actually maize or corn. It also predicted urban when it was actually maize, and also predicted onion when it was maize. But still 33, so it's not ideal, but generally I think it's getting the idea. But we still think we would probably add some more samples here for corn, just because it's getting some wrong, not all, but there could be improvement. And one thing we've got to think about when we look at the in-situ data, so look at it in QGIS. When we look at the data we had, we know that we can see straight away here that all our in-situ data is already grouped in one geographical area. So what I was saying before, when we've got a crop, when we've got multiple, or all your crop samples in one area, they're going to be, to an extent, spatially autocorrelated. So they're going to be similar to those around it. So you can see all these classes here, or these crops here, these are all the same crop, but they're so close to each other, possibly under the same management, under the same regime of fertilization and irrigation and everything, they're probably very similar. And so these data points, although it's artificially, in a way, showing that you've got more data points, when really that could be treated as one or a few. We didn't, because they're all similar. Yeah, they could be treated as one, and it would be better to have more samples in another geographic location where the same crop might be looking different because, yeah, many reasons, as you understand. So that's a key message for using census is to really spread around to get the variability of the crop. So the algorithm knows that it can vary, because then if it just looks for a crop that looks exactly like this, because that's all it's seen, if it varies just slightly, say it had a hard week and didn't get any rain in another area, it might then be different enough that it's classified as a wrong crop. Yeah, so that's how we can use this confusion matrix to ascertain which crops to look into. There's also, so another thing that comes with the confusion matrix is the accuracy scores. And so you've got recall and precision, and then F-class score. So these can be confusing, what they exactly mean, and they're always different. Sometimes they're like the opposite. But yeah, it's always good to understand them. So the best way I think of it is pretend we've got just say a hectare that we've mapped, just a small area, and there's 3 polygons in there. Well, 3 polygons that were used for testing, not for the prediction, so it's unseen. And say we're just looking at corn, we're just looking at precision, recall, the accuracy of corn. Let's say that the algorithm, to keep it simple, algorithm predicted it all as corn, this whole hectare. So we look at the precision, and we think of that from the perspective of the in-situ data. So I visualize it in my head because it works better for me. I think of it like coming from underneath, so what's really there. And we're looking at corn. So we look at the polygons that we know are the in-situ as corn, and that's 2 out of 3. But we're only looking at the ones that were labeled as corn, which is only 2 of them. And we look at those, what was predicted? Yes, corn. So we're only looking at those 2 polygons that were corn, perfect score. Then we look at the other metric, and we think of it as the prediction, or we come at it from the predictions perspective. And I always think of that as coming from the top. So what was predicted, not necessarily what was there. So we go from the top, from the prediction, and we look at the polygons, the in-situ data that was predicted as corn, which is all 3 in this case. And then we look what was really there, and only 2 of them correct, 1 is wrong. So that way it gets a lower score. So the precision will be 1, and the recall will be slightly less, between 0 and 1. I can't say exactly actually. And then the F score is, I can't explain it exactly. It's basically a combination of those 2 with an adjustment for random chance. So if it was 0, it would basically just complete random chance that it got it right or wrong. So this is just loading. This was just in case I wasn't able to use QGIS to have a look at the outputs from Centre. So it's quickly just also just for later use of this notebook, just to have a look at what actually came out. But again, this is subsetted. So you can see compared to our earlier attempt with just one image, that it's done much better job. It's less noisy. The fields are defined, the features are defined. But you can see on the confidence straight away that this is most likely forest, and this is most likely croplands, and so most crops seem to still need some work with the in-situ data. But I have to say again, this was a trial run. We had only 3 or 4 crops, as I showed before. So this is the reason why there's still some low confidence, because to make a real, let's say, not official attempt, but to make a real attempt to get a good map, then we really have to make an effort with the in-situ data, make sure everything's covered. And I think that might be it for today. Yeah, any questions? Nope. Happy?
We'll try our best. Actually, I was gonna ask what you're gonna do with the problem areas, those cropland areas that were classified as forests. So I think the answer is written at the end of the.
Yes, exactly.
Okay, we need to add more samples.
Exactly. So as mentioned before, it's reiteration. Yeah, it's really, it will take a few shots. You can't expect everything to be perfect the first time. Yeah. Okay, then I'll hand it over to Marianne. Yep. Cool. Thanks, Ben.
Okay. So thank you everyone for joining us today. So as I mentioned at the beginning, so we will have the last part of the crop training series will happen in August. So from 4 to 8th of August, so the dates are now being finalized because we'll have the last part for all the trainings in the same week. So we need to fit this in 1 week. So a quick reminder also, if you want to get a certification at the end of the series, you have to go and register to the CopPhil digital CopPhil platform, where you will have the link in the presentation. I can actually maybe show it again. It's from the beginning. Yeah, so basically you have to go to this CopPhil digital platform. If you have any questions, doubts, remarks, just come to us. You have and actually through the platform you can also ask some questions. There are some threads to do for several discussions on the different topics. So Dominic will also have an access, and he can actually access and see the question there. So there can be technical questions. It's okay. What else can I tell you? So again, so we'll be having the forest practical training next week. So we are now sending the invitation, and if some of you have applied, you should receive confirmation or waiting list email that we are sending now. And yeah, and I think we'll see you at the next session. We're very happy to have you here. And if you have any question, we still have a few minutes if you want to come and talk to Dominic or us, but I'm not sure I will be able to answer your questions. But yeah, and before you leave, we'll make a group picture, if that's okay for you. So we can see how this training went also. Thank you very much for coming.